Alright, class. So today we are going to start another chapter of our stress analysis course, which is the deformation produced by stress in a body. Uh, although the thing is that many of you might think that all we have to know is stress, whether something is capable of uh, uh, tolerating a certain level of stress is enough, but that's not the case. At some applications we do not want deformation to produce in our member, simply because even by a slightest deformation things can lead to accidents, or perhaps deformation produced is much larger than we can tolerate, such that it can produce accidents and can lead to situations which are undesirable. So in order to avoid that, we have to know strains at uh, at the smallest level, so that we can actually know if it is in our tolerable limit or not. Okay, so we're going to go through that process of actually finding it and the various factors that are involved in strains. But overall it is related to previous chapters. So if you have if you have a good basis, if you have a good base in the previous chapter, this chapter will not be that hard for you, because even in this chapter, if you know one equation, it is easier for you to to predict other equations as well. Okay, so before I continue, I would like to mention that there are two types of displacements. So we have when we have a rigid body, we have a displacement known as the translation motion. Okay, translation motion, and we have a displacement motion. So in the translation motion, although it looks similar, but for the sake of this chapter, we are differentiating. The translating motion simply represents that one body as a whole, with all its points, change its position from one place to another. But in displacement motion, uh, rather than the full body displaces, there are certain section or the certain points inside a body that moves from one point to another relative to other points as well. So this is this displacement motion is the focus of our interest. Now the thing is that when we a body is composed of many points, right? Infinite number of points, and also that the coordinate system in which we want our body to behave, that coordinate system is also defined by us. So this coordinate system can be of 3 dimension, it can be of more than 3 dimension as well. Okay, so when we have a situation like this, when we want to know, if let us assume that we have a quantity x, and this quantity x is changing, it's becoming x dash, and we want to know what are the effects of x dash on the various coordinate system possible. So x, y, z, k, and so on. Is a coordinate system which we define. So the x dot will going to have certain effects on x, or let's not call it x, let's call it p. P will be much better. So what are so the change in p will going to have an effect on x, on y, on z, and k, and so forth. So in order to actually calculate the effects of one quantity that is changed on multiple dimensions, we actually use what is called as the Taylor series. So the Taylor series is actually a mathematical, you can say, it's a mathematical approach in which we try to calculate a change in a certain quantity when its effect is produced or experienced on multiple dimensions. Okay, so we have here what we have considered is this situation. Okay, so in this situation you can see that we have point P and point Q located in a certain cube which has dimension delta y, which is alone y, delta x alone x, and delta z alone z axis. And whatever the change produced in x, it will be called u, and whatever change produced in y, it will be called v, and whatever change produced in z, it will be called w. So we have u, v, and w. So after the point changes, after certain application of force or stress, the point changes from P to P dash or P star, and Q changes from Q to Q star, as shown in this here. Okay. So when the point changes, the dimension, or the you can say the dimension of the cube also changes to y. Delta y changes to y dash, delta x changes to delta x dash, and delta z changes to delta z dash. Okay. In order to record the changes, what we do is that we have said that the space which the body occupies on the x-axis will be u, and on y it will be v, and on z will be w. So if the PQ changes, its corresponding impact on the dimension also changes. So the new dimension will be for u, it will be u dash, u star, it will be v star, and it will be w star. So in order to the change of u along every dimension, we use the Taylor series. So we have u star equals initial u and partial change in u with respect to x. So this is partial change in u with respect to x multiplied by the change, or the you can say the original dimension of the cube, which is delta x. Similarly, change in u with respect to y, change in u with respect to z, and so on and so forth. Depends on how many dimensions we have. Okay. We can have higher dimension, we can have delta x square and delta y square and delta z square. Okay. But what happens is that when you have a very small element which is very small, which is of very small value, taking a higher power on that smaller quantity will going to increase its insignificance, or in other words, the zeros will going to get increased as it is amplified. Hence we can approximate it to zero. When we approximate these quantities to zero, we have the u star will going to change into u dash, and v star will going to change into v star will going to reduce to this, and w is will going to reduce to this. Okay. Because we have neglected the higher powers, so if the cube is straight and such that the 2 points of the cube are relatively very close to each other, so after deformation they will going to stay linear. So the linearity will going to uphold, and higher power will reduce to zero. Okay. So from the definition of normal strain, we know that delta x bar minus delta x upon delta x. So we change this into this, and nothing to explain here. And now what happens is that now we are going to make an equation x bar. So this, if you see figure 2.2, this is, we have initially PQ, and this changed to P star to Q star, changing delta x to delta x dash. Okay. So we know that if we have a hypotenuse, it will be equals to u square plus b square plus w square. ठीक है, यही होता है ना. So what we have done, so we have initially w u and this is, I guess, delta x is equals to u, but when it changes, ठीक है, it change along every axis. So we calculate the change. So along x it will be 1 plus du upon dx multiplied by delta x. ठीक है, this will be I guess u square, and this this will be the u part, and this will be the v part, and this will be the w part. ठीक है, so we did this and we get this equation. ठीक है, now substituting equation squaring equation b and substituting equation c, we get this. ठीक है, so we put this thing right here, I mean right here we get this, and we expand it to common of delta x square, and finally we get this equation. This is just simplification, there is nothing to understand. I mean there is no there's not so much of a technical thing here. ठीक है, so if I can predict sigma of xx, I can also predict sigma of yy. ठीक है, so it will be u, then it will be what comes after u, let's say u v w. So if x has u, y will have v, y will have v. If u is present here, then v will going to present here, v is present here, so w will be present there, and w is present there. What will happen? U will be present there. Okay, so if we move here, then if we reach w, we're going to reverse our course. Okay, so that's how, if we know one equation, will be able to predict the next equation. Okay. All right. One thing I failed to, or I forgot to tell you, is that the reason why this y tends to, wait a second. So the reason why is it's y tend to 0 and this y tends to 0 and this z tends to 0 is because in your book it is written that if you see that figure 2.2, this figure, the only change that is being observed is in the x. So what they have done is that they have gone from you can say a more simplistic version of this problem. Okay, so they have gone from the transition from a 3-dimensional change to just 1-dimensional change to actually get to the root of the the root of the calculation. So which is why you can see that y tends to 0 and z tends to 0. Okay, but if this had not been the case, we had no reason to actually cancel delta y and delta z. Okay, so now let's move on to this part. In this part you can actually see that we have PQR line. Okay, this line, and this line, what happens is that this PR line tends to rotate in this direction and then in this direction, and as a whole it then rotates towards z. Okay, so in R, first in R, then Q, then in rotating in z direction. Okay, so this is displacement as well as the rotational you can say a rotational displacement. Okay, so it was at point it was at this point first, point P, but then it moves along the point W. Okay, so and then it moves a little upward according to the situation is given. Now when we were in first year, we actually studied a law of cosine, which says that the angle between two intersecting lines, in our case it's PR and PQ, P star R star and P star Q star, the angle theta star is actually the product of its cosines. ठीक है. So it was like, if you remember, we have three cosines, L square plus M square plus N square equals 1, right? So the cos of theta star should be L1 L2 plus M1 M2 plus N1 N2. ठीक है. So L1 will be L1 M1 M1 will be the direction cosines of P star Q star, and L2 M2 and N2 will be direction cosines of P star to R star. ठीक है. So what we have done is that we apply this cos, we applied the law of direction of cosines and came up with this complex algebraical expression. It may look a little complex, but bear with me, it's extremely easy. So it's, if you can see here, it is this factor divided by this factor. ठीक है. Divided by this factor. And similarly, we first deal with the x part of the P star Q star, and then we'll deal with the x part of the P star and R star. So the x part of the P star Y star is this is the x part, and this is the hypotenuse. ठीक है. So this will be divided by this, and you will going to get this. ठीक है. Similarly, you will going to do this with y, and similarly you will going to do this with z. ठीक है. So after getting this expression, what we now come to is the definition of the strain. We are finding strain in the xy direction, so it can be written as pi by 2 minus theta star. So if you take sine on both sides, this will be converted into cos theta star, and you put the value of cos theta star from here. ठीक है. So this, and if you take the common, this will be the final expression. ठीक है. Now what you're going to do is that you're going to क्या कहते हैं, take theta x bar and theta y bar as this. ठीक है. इसको ऐसे करना है. Then what we have done here, we have actually get to this expression by taking sine over this side. So we get sine inverse or arc sine theta, and then du into dy multiplied by 1. So we get this. ठीक है. And then du in d square u and dx dy. So this will be here. Similarly, dv upon dy multiplied by 1 will be here, and so on and so forth. We get this expression. ठीक है. And so one thing with this delta x and delta y will be cancelled out by this. ठीक है. So we finally get this expression. So if we can predict the xy, we can do this for yz and zx by simply using our the forward direction transformation, which is just my made up transformation. So u goes to v and v goes to w. So whatever is u in the previous expression will become v in the next expression, and will become w in the next expression. So by using this rule, we can actually figure it out, both zx and yz. ठीक है. That normally the type of engineering problems in which we encountered, what is observed is that if we neglect the higher order differential, it has the effect of limiting our line segment, which is responsible for deformation, and also since under these conditions, it can be assumed that the products and square of the displacement gradients will be so small that we can actually neglect the higher order derivatives, or we can neglect their products. So by using this assumption, if we can further simplify equation 2.2 and 2.3, it will going to come out like this. Okay, so this is not a simplified form, this is its simplified form. By using the assumption which I have told you to actually neglect the higher power derivatives and neglect the derivatives which are the products, so we're going to get these type क्या कहते हैं, under the assumption our expression will be reduced to these following 6 expressions for normal strain and shear strain. ठीक है. Now the strain equation for transformation, so what we originally had, we actually assume that we have a line PQ which change into line P star and Q star with a change in displacement delta Z to delta Z star, delta X to delta X star, and delta Y to delta Y star. So in order to use this in our strain formula, we simply put the values in the formula P star Q star minus PQ divided by PQ. Nothing to explain here. So PQ is actually x square plus y square plus z square. It's simple. This is just simply the expression, and for P star Q star this will be the expression. ठीक है. And now the delta star will be equal to 1 plus du upon dx delta x, du upon dy delta y, du upon dz delta z, which is simply the Taylor series. ठीक है. Similarly for y we have, for z we have this. Now putting all of this in right here, so by putting all of this here and क्या कहते हैं sorry. All right, so after getting this sorry, so after getting this, wait a second, after getting this expression, and we simply just rearrange this equation to get this one in this form, and then we finally put the value of P star Q star upon PQ. So so we already established the value of P star Q star, and the value of P star and PQ whole star will be this one. So putting it and simplifying it, we get this. ठीक है. Sorry. Now we actually know that we have cos square ypq cos square z square. This can be equal to 1 because this is cos square alpha cos square beta cos square gamma equals 1. So this is a law of cosine, if you remembered, you studied in your second intermediate. So by using this the property, we can cancel it this with 1 after we क्या कहते हैं expand the formula, because it will come out to be like delta EPQ square plus 2 EPQ plus 1. So this 1 and this 1 will going to be cancel out, and this will going to get to 0. Okay, and this 2 will be taken out as common, this 2, and it will be cancel out with this 2. Okay, so we are going to end up with this expression, I guess. This is the expression. Okay, this is the expression we are going to end up after simplifying it. Now this is for PQ, but we can generalize it to any x bar direction. So for x bar direction, the thing that will going to be changed is, alright, one thing more is that, wait a second, alright, sorry for that. So this dava u upon dava x is equals to, if you see here, it's okay, so we just are going to substitute this with this. and this is what we have precisely done here, and finally got is the next expression, finally gotten this expression. And then using our same transformation process, u goes to v and goes to w, v or x goes to y, goes to z. We came up with this expression, and if you can see the contrast between this and this, you can see there's a very striking contrast. There's a very striking similarity of the stress equation and its corresponding strain equation. So you can come up with, if you know the stress equation, you can also come up with the strain equation as well. And this is what precisely has been. So 2 tau xy will be can be correspond to gamma xy, and the expression of the shear strain, it's given to you here. So just remove it. It's just for the sake of comparison, I just copy pasted it from the previous slide. Okay, so if you can see here, these two expressions are quite similar. So if you know this expression, you can also come up with this expression as well. Okay, so this is just all about finding the strains, the shear strain and the normal strain. So, and it is also very much related to the concept of shear stress and normal stress, which you have seen earlier. Okay, so if you closely look at these expressions, you can actually find the relationship between the two. Okay, so moving on to the new topic, we have principal strains. So just as we have principal stresses that has no so just as we have the process of normal stresses in which there are no shear strains, similarly the strain produced by the normal stress will be called as the principal strains. So the strain produced by principal stress will be the principal strains. So what we are going to do is that we are going to simply convert this expression of normal strain to this expression of shear stress. That's the only difference, that some expression will be replaced by another, other than the fashion, or you can say the overall relation between the same. So you are going to get in this expression you get sigma 1, sigma 2 and sigma 3. Here you will get E1, E2 and E3. Okay, so and finally just as we had invariance here, we are also going to have invariance here. Okay, so even that is quite comparable. Okay, so moving on to the next topic, we have the compatibility. Alright, so now what we are going to do is we're going to see the compatibility questions. The compatibility questions are the questions that actually checks whether a certain system that is going under deformation is compatible or not. So the idea behind this concept is that sometimes when a stress is applied and a deformation is produced, we tend to get voids at the micro level. Okay, so in an ideal condition, if the stress is removed, the system should go back to its place. But if the voids are present, the system will not revert back to its original shape, but to revert back to a different set of state, which was not the original state to begin with. Okay, so in order to check whether a certain system actually behaves in such a manner, we have invented a sort of, you can say, a compatibility checks to ensure if we are dealing with a system that is compatible. So we have these equations, and we are going to learn how we actually arrive at this arrive with these equations. So